Okay. So it's being recorded. So can people see the page, I guess?
Yeah.
Okay, cool. So let's see what happens. So, okay. So, okay, so what was I even talking about? So let's see here. What was I doing? Oh yeah. So I was talking about, so can you read this?
Yes.
Yeah.
Okay. So I was talking about undetermined coefficients. And the, wait a second. Okay.
If you're able to use your internet on your phone, is it possible you can just turn on hotspot and connect it on your laptop?
Yeah. So I'm planning to do that, but actually, what it's doing right now is it's encoding the previously recorded part of the lecture that I don't want to entirely lose. So I will do that in like 5 minutes. You could talk about the stuff without writing much. That's hard. Okay, let's try this. Let's see what happens. I'm going to put a box on the page on this, I guess. So undetermined coefficients basically skip. And now I'll get to the, I mean, you can read about it if you want. It's the same idea. You just you restrict to polynomials and the obvious thing happens. Okay, so now I'm going to talk about the more interesting thing, which is why are we doing all this in the first place, right? So why are we interested in solving a system of linear ODE like this? So there are 2 reasons. I mean, the main reason is I'll tell you call it a dirty secret. So dirty secret because it's something that looks like it shouldn't work, and it's extremely powerful. And I probably should have told it to you earlier, but here's the dirty secret: is that you actually, once you can solve a system of first order ODE, you can solve any nth order ODE by reducing to a system of first order ODE. Okay, so what I'm proposing sort of looks like this: that given any, let's say, given one single nth order ODE, and that means in one variable. So, for example, given an equation, so what's the example I had in mind? Given, for example, this equation, here's an example of a third order ODE, something we haven't really seen in the course: y triple prime plus 7y prime minus 3y equals, let's say, sine of t. There's a way to convert it into a system, so multiple, of n first order ODE in n variables. So in this case, this would be turned into a system of 3 equations in 3 variables. So it's like a trade, right? So what you gain is you turn this nth order into a first order. This is the gain. But you pay for this, right? You pay by adding a bunch of variables and a bunch of equations. So this is a very powerful and simple idea that's often called the linearization trick. And let me now demonstrate it on this example. Okay, so just a second. It looks like my computer somehow came back. What? Oh, okay. So I found out what happened, which is that my girlfriend literally canceled the internet just now. So anyway, okay. We were planning to get a faster internet, but anyway, whatever. So, so I guess there's no internet. Anyway, so let me tell you what the linearization trig is. So, okay, so let's demonstrate it on this example. So what's the idea? Well, let's look at this equation. Okay. Now, the thing that's bad about it is it has some higher order derivatives like y triple prime, right? And we don't want that. So the idea, which is very simple, is introduce new variables. So let x1 be just y, the function you want to find. Now let x2 be a new variable, which is going to encode y prime. Okay. And then let x3 be a variable that encodes y double prime. So you introduce a new variable up to the highest derivative minus 1. So you have 3 variables. So now the nice thing is, if you have these variables, if you somehow define them, then you can write this equation as a first order equation. Because y triple prime is just x3 prime, right? Plus 7, now y prime, that's just x2. And 3y, that's just x1 equals sine of t. Right? So these are all, of course, functions of t. Okay? So this is now a first order equation. But there's something I've paid for this, which is in order for this to have exactly the same solutions as the previous one, I need to satisfy actually 3 equations. I need to satisfy this equation, but now I actually generated 2 new equations because x2 is equal to y1 prime, so x2 is actually equal to x1 prime. Right? The relationship between x1 and x2 is important. Otherwise, I could get all kinds of new solutions. And similarly, x3 is equal to x2 prime. Right? So actually, I have 3 equations now. But what I gained is that the highest derivative appearing in these equations is first order. There are no higher order derivatives appearing. Okay. So now, so what do I get? I have a system. Now let me just write it in a form that makes it clear it's the type of object we've been studying. I get x1 prime equals x2, x2 prime equals x3. So that these are these first 2 equations. And then x3 prime equals this third equation, which is the original equation, but I move everything to the other side. So that's 3x1 minus 7x2 minus sine of t. Okay? And now the key property is, so let's the original equation is star.
We can't really see it.
You can't really see it? Okay. Can I move my camera down? Okay. Just a second. Okay, my hand. I'm actually literally holding the camera, so my hand is getting kind of tired. Let's try this. Oh, whoops. Okay, that doesn't work. Okay, is this more visible?
Yeah.
Yeah, that's great.
Okay, actually, yeah, this works better for me too, because now I don't have to hold it anymore. So the lighting is not great, I guess. Maybe this is better. Is that better?
Yeah.
Maybe it's the same. Okay, so the key property is that I didn't add any new solutions when I did this. Any solution y of the original equation gives me a solution of this system of equations just by setting x2 to be y prime and x3 to be y double prime. And similarly, any solution of the system double star gives me a solution of the system star, because that's just what these equations say. If I substitute the first two equations into the last one, that's just star. So these have the same solutions. That's the key property. And just to make it very clear, this system double star is actually of the type we've been studying, right? It's x of t equals some 3 by 3 matrix. So, okay, let me just write those down. So it's d by dt of x of t. D by dt of x of t is the vector x1 prime of t, x2 prime of t, x3 prime of t. Okay? And now these coefficients are going to be what appears over here, right? So what is it? X1 prime is just x2, so you get 0, 1, 0. X2 prime is just x3, so you get 0, 0, 1. And x3 prime is 3x1 minus 7x2 and 0, x3. And now you get a plus sine t here, right? So you get a 0, 0 minus sine t.
I think sine of t is positive.
Excuse me?
I think sine of t is supposed to be positive.
Sine of t is supposed to be positive, correct. When I move this to the other side, it's plus, so this is plus. Thank you. But that's great, right? This is an equation in normal form with this matrix A. So this is kind of amazing. You can solve any order ODE by solving these linear first order ODEs. So, I mean, when I first saw this, I thought that, this can't possibly work, but that's actually quite a powerful thing. So what's the, so I'll just say what you do in general. Okay. So in general, if you have a first order ODE like an nth derivative of y plus an minus 1 and minus first derivative of y all the way up to a naught y equals f, you can turn this into n equations by making the following substitutions. So x1 is equal to y, x2 is equal to y prime, which importantly can be written just as derivative of x1 prime. Then x3 is equal to y double prime, which is equal to derivative of x2 prime, all the way up to xn is xn minus 1 prime, right? So that gives you n minus 1 equations. The first equation is just a substitution. It's not really an equation, it's just renaming the variable, plus the original equation, which is, if after rearranging, can be written as xn prime equals 1 over an times minus an minus 1 xn minus an minus 2 xn minus 1 all the way up to minus a naught x1 plus f over an. And that's your n equations, right? This is a normal form equation. So this is extremely powerful. You can solve any differential equation using this method.
Could you move your paper to the left a little bit? Thank you.
Okay. Can you see the whole thing, or is that? Okay, I'll just write in a smaller square, I guess. Okay. Okay, so that's one reason to study these. And here's an important special case, which may be of interest since we spent 2 lectures studying earlier. Is this a good box? Or maybe it's too small. We'll see. So a special case is, what about second order? Well, according to this, you can solve this also using this different method. We already have one way of solving this. But now you could also solve this by linearizing it, right? So how do you linearize it? Well, you set x1 equal to y, x2 equal to y prime, which is now x1 prime. And now this equation becomes a x2 single prime plus b x2 plus c x1 equals 0, right? So now, if you write this in normal form, what is it saying? Well, it's saying x1 prime, x2 prime is equal to submatrix times x1, x2. And what is that matrix? Well, the first row is just going to be 0, 1. The second row is you're going to move everything to the other side. You're going to get minus c over a and minus b over a, right? So according to this, you should be able to solve this system using, by computing the eigenvalues of this matrix A, right? But what are the eigenvalues of this matrix A? Well, the characteristic polynomial of this matrix is this determinant, right? How did I get the matrix? I literally combined these equations. Right? So I moved all the primes to one side and just wrote them in matrix form. Okay. So now, oh wow, my phone is overheating now. Anyway, we'll see what happens. So if you compute this, what do you get? You get lambda times b over a plus lambda, the minuses cancel, plus c over a, right? Which is lambda squared plus b over a lambda plus c over a. And does this look familiar to anybody?
This looks like what we did in chapter 4, I believe. It was.
Yeah, it's the same as the auxiliary polynomial, right? It's just the auxiliary polynomial divided by a. So it's a different way to solve second order ODE. So another reason why this is a dirty secret is that it now reveals that I didn't actually need to tell you all that stuff about factorizing differential operators, because we could have just done this. Except that's not entirely true, because this only works when it's diagonalizable, right? We didn't explain how to do it when it's not diagonalizable. That's why I told you about the other method. Okay? So that's the connection between this and the chapter on second order ODE, that if you encode the second order ODE as a system of linear ODE and use this method, you will get solutions, e to the lambda 1t, okay, times the eigenvectors. So times v1, e to the lambda 2t times v2. And if you calculate the eigenvectors, so now we have to think, what's the relationship between this new matrix problem and the original problem? So solutions, so the relationship is the solutions of, so let's call this original thing star, are the first coordinate of solutions of double star, right? So double star is this. right? Because of this equation, x1 equals y, right? And so if you compute the, you have to actually compute the eigenvectors. And okay, if you do this, you get that these matrices always have very special eigenvectors whose first coordinates are always 1. Can always, I mean, well, they're always, they can be taken to be the same under some normalization, maybe is an important thing. Okay. I mean, in some sense, it doesn't matter what the first coordinates are actually, because as long as they're not 0, because you can scale the eigenvector to make them. Okay, so the summary of this is that this is a, what does B, sorry, this is T, not B, sorry about that. Yeah, sorry, it's, yeah, I'm somehow not used to this. Handwriting is really bad, but okay, so that's a special case. What's another motivation? I mean, that's a pretty solid motivation according to me. You can solve any first order ODE using this method. So let's draw that.
Professor, can you explain again like the last concept of how does the solutions of star equals to first coordinate of solution?
So if you look back here, right? The key thing that gives the solutions, the relationship between the solutions is this equation, x1 equals y, right? So that means if you have some x1, x2, that's a solution of double star, that implies that x1 is a solution of star. Does that make sense?
Yeah, thank you.
Yep. Any other questions? Okay. So, yeah, what was I saying? I was saying now that there's another motivation for doing this. The second motivation is, I was going to show you an animation of this, but my computer's not working, but it's the same as last time. Remember that picture I showed you of the 2 blocks? So you can use this to study the motion of these 2 blocks in a very nice way. So again, let's describe this using ODE. So let's say these are both unit masses for simplicity. And let's say the position, let's say I'm measuring their distance from the equilibrium position with some variables y1 of t and y2 of t. Okay. And let's say that there's no friction. Okay, so that's some sort of simplified equations of motion. So the only forces acting on these are the spring forces, right, that come from Hooke's law. So let's look at what those are. So net force on the first block. Well, according to Newton's law, that should be y1 double prime, right, at time t. F equals m, m is 1. But it should also be equal to the force from these 2 springs, right? So let's say these are 2 springs with spring constant K1 and K2. So these zeros are the equilibrium positions of both springs. So if you compress or stretch the springs, they're going to exert a restoring force, right? So by Hooke's law, well, I'm going to have a force from the first spring that's minus K1 times Y1. Okay. And now I'm going to have a force from the second spring as well. And that's going to be minus K2 times Y1, but minus Y2, right? Because, I mean, if Y, really what I care about is the distance between these two things. I don't care about the absolute value of Y1. and that's y1 minus y2. Okay. So I always get confused by this. I mean, this is actually why I dropped out of doing physics, because I could never figure out the signs in these diagrams. So let's see. Y1 minus y2 is going to be negative in general. So this force, okay. The sign of this force should be negative in y1. That is correct. As y1 gets bigger, the force acts in the negative direction. Okay, fine, this is correct. Then again, I have the net force on the second block. That's y2 double prime. And that's only getting acted on by this one K2. That's going to be minus K2. Again, I'm confused about the sign. Let me check. Well, this is just displacement from the equilibrium position. Yeah, so it's going to be y2 minus y1. Okay. So the motion of the system is described by the system of second order ODE, right? You have two second order equations. But now the amazing thing is that actually what I described, not only does it work for one second order ODE, you could do the same thing for two second order ODE, right? Nothing is stopping me. That linearization trick is very powerful. So what I'm going to do is introduce some new variables. What are the new variables? Well, x1 is just going to be y1. x2 is going to be y1 prime, which is just x1 prime. Then x3 is going to be y2, my second function. x4 is going to be y2 prime, which is x3 prime. So now I have introduced two equations, right? Two equations relating my new variables. But now I'm going to get two more equations from this, right? If I write them in the new variables. So let's do that. So this is going to be the equation. So y1 double prime is just x2 single prime. This equals minus k1 x1 minus k2. So y1 is x1, y2 is x3. And the second equation becomes so y2 double prime is y2 prime prime, which is x4 prime, equals minus k2 times y2 minus y1, which is x3 minus x1, right? But now the point is, if I take these four equations, right, these four equations, and I move all the primes to one side, this is literally an equation of type x prime equals ax for some 4x4 matrix A. So this is way more than, we asked for, right? Not only can you solve a single higher order ODE, you can actually solve a system of arbitrary order ODEs using this. It's very powerful. And the point I really wanted to make by showing you this example is that in reality, a lot of physical systems can be modeled as a bunch of springs connected together in some way that are vibrating, right? And what this is telling you is that the motion of all of those systems can be reduced to finding eigenvalues of some matrix. Because you can write all of them as a system of ODE. So what I'm saying is that physical systems can be modeled as system of ODE, usually second order. Most laws of physics are second order, which then can be turned into an eigenvalue problem. And this explains the physical meaning of eigenvalues. Eigenvalues are, vibrational modes of physical systems. I mean, a lot of the, things you see in physics and chemistry, like emission spectra of atoms and, all kinds of other things, they're really just eigenvalues. And it comes down to this fact that when you encode when you want to solve differential equations, you can all
Who's the host? Hello? Hello? Oh, God. Any of you willing to fill in the time? Okay, never mind. Sorry.
So what we should do now?
Anyone in 61A by any chance?
I mean, a 61 in previous semester.
Professor?
Is somebody playing music or something? Or anyway, okay. I'm not sure what happened. I hope it's still recording.
Yes, we can see your face.
Okay, well, I might as well tell you the cool thing. So let me just tell you quickly. Okay, so there's one loose end that we left here. So this method seemed incredibly powerful. You could solve a huge class of this differential equations, systems of differential equations. And the question is, what if, so suppose you have x prime t equals ax. The question is, what if a is not diagonalizable? So this has an incredibly cool answer, which we won't do in any detail, which I only learned about in grad school for some reason. And the answer is, I'm going to define the exponential of a matrix. So e to the ta, so A is an n by n matrix. Define this to be the usual thing. Okay, there's some issues about what it means for that to converge, but let's say it converges. Okay, so that's called the matrix exponential. It's an n by n matrix, right? Any questions about the definition? Okay. And now what's the amazing thing? Well, what happens if you differentiate this? Well, you differentiate each of the terms, right? So you do d by dt of the series. Sorry, there are t's everywhere. The t's are important, right? It's e to the ta. So you have So now what happens if you just differentiate it term by term? Well, the first term is 0, so you get 0. The second term is just a. The third term, you differentiate the t squared, that lowers the degree but introduces a 2. So you get t a squared over 1 factorial. Right. Now the third term, again, the same. The 3 cancels the 3 factorial. You get t squared a cubed over 2 factorial. Yeah, that's just the Taylor series. And now does anybody recognize what this is? It's just a times e to the ta, right? Every term has an a. If you pull it out, you get this is a times 1 plus ta plus t squared a squared over 2 factorial. So this is a times e to the ta. That's kind of amazing. That means that for matrices, actually the solution is just the same as for scalars, right? This is the same as what you have for scalars. But what does it mean for the differential equation? It means every column of e to the ta is a solution of the ODE. And you can prove that they're linearly independent. So in one shot, this gives you a basis for the solution space for any A. The downside is you have to have an infinite series of matrices. But I don't know, I thought this was very cool. If you want to read about it, it's in 9.8. This is optional. Anyway, thanks for bearing with me. And yeah, hopefully I'll fix the internet. Okay, bye.
See you.
Thank you very much.
Thank you.
Oh, Professor,
Mhm.
I have a question regarding the final. So on Piazza, it was mentioned that there